great pleasure to introduce Misha Kajvan, friend and collaborator. And Misha got his bachelor's in math at Harvard. He did his PhD in computer science at Princeton, and he's been on the faculty at Johns Hopkins since 2004. Misha is a leader in the growing area of three-dimensional geometry processing. So he did a lot of seminal work on shape matching, symmetry detection, surface reconstruction. Perhaps one of the biggest claims to fame is developing the Poisson reconstruction algorithm used for turning scans into 3D meshes. This has been cited several thousand times, so you may very well have actually used this algorithm, even if you didn't realize you were using it. And generally, Misha is known not just for coming up with great algorithms, but also providing the community with really great code, real implementations of his algorithms that actually get used. Nice thing to do. For instance, he is the winner of a SGP software award, and most recently, NASA has been using his code to reconstruct the surface of Mars. Also, in the more traditional image processing domain, Misha's worked on fast solvers, multi-grid solvers, and things like this, which recently been used to do terapixel image stitching for images from the Sloan Digital Sky Survey. And today, Misha is going to talk about the many interesting connections and questions about how to generalize a lot of the things that we know or want to do with images to curved surfaces.
Thank you, Keenan. Thank you. You guys can hear me? I'm coming over a cold or off of a cold, so I'm going to try to speak up. So first of all, thank you. If anything, your life here is anything like my life at Hopkins, you are deep in the midst of faculty hiring, which means that you have more talks to go to than you have time for. So I appreciate the fact that you guys are actually out here for this talk. So thank you. What I want to talk about today, as Keenan suggested, is sort of transitioning from signal processing on images, something that we know how to do well, sort of the community has really done some fantastic things with, and pushing that to working with signals on surfaces. In particular, I will look at 4 problems. One is sort of this gradient domain blah problem, stitching, sharpening, smoothing, whatever, just stuff in the gradient domain. Here's an example. Here's a picture of Haifa that I took with my camera on a tripod. It's a panorama. You can see all sorts of discontinuity, and sort of a classic problem is to try and get rid of the discontinuities, synthesize something like that. Okay. Another application is line integral convolution. You have a vector field, and you would like to visualize it somehow. You want to show people sort of where the streamlines are, how it behaves. You want to somehow do some sort of evolution that gives you this nice visual. Another problem is in the domain of shock filtering. So this is an established technique from, I think, the 80s. You have an image, in this case a tiger from the Washington Zoo. I'm going to try and show you sharpened images, but things are blurry on this monitor, so hopefully this will work out. Here's a zoom in of the eye, and you want to do something in order to sort of make the boundaries clearer, crisper, to sort of highlight the detail of what's going on. And then actually close to home for you guys is the notion of optical flow. If you have 2 images, a source and a target, you want to synthesize some sort of in-between images. You would like to figure out how pixels move from the source to the target so that you can create these in-between shapes. And my goal in all of this is to sort of look at how you take this to the domain of mesh processing. Okay, good? All right. So before I do that, I'm going to talk about 2 tools, pretty basic tools, not mine, that just need to be covered in order to be able to talk about what we're going to talk about later. One is going to be the screen Poisson equation, and the other is going to be flow fields and flow lines. Okay. By the way, if you have questions, feel free to raise your hand in the middle of the talk. It's not imperative that we get through everything. It is more useful if I can answer questions if you have confusion. So please, if you're confused, let me know. Okay. So here's sort of the formulation of the screen Poisson equation. We're given some sort of signal G, some target signal G, some target vector field V, and our goal is to find a function f that satisfies, that minimizes this energy. And this energy is composed of 2 parts. On the left, you see you want f to be close to g, your input signal. On the right, you want the gradient of f to be close to this vector field v. Okay, those are sort of the two things that you would like to satisfy simultaneously. So if we didn't have the right-hand part, the energy is clearly minimized when F is equal to G. That's a trivial case, but somehow this combination is what makes this problem interesting. You can go through the usual rigmarole of formulating the Euler-Lagrange formulation of this problem, and this ends up being a linear system where you have the identity matrix minus the Laplacian times F is to be equal to some multiple of G plus or minus the divergence of your vector field. Okay, you can show that. Good. So that's the Screen-Poisson equation. Good. The second thing I want to talk about is flow fields. So again, working in a 2D domain, you have a vector field, and you define a flow line as a curve that follows the vector field. So at time t is equal to 0, it's just at the point where you start. And then as you move around the curve, if you were to evaluate the derivative of the curve, that should match the value of the vector field under that point, right? So it looks something like that. Good, 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 good. And you can use this to advect signals. So if I have a signal like the snail on a leaf, and I want to advect it under the vector field, what I would do is to find the value under the advection. I would walk the vector field, so to find the value at, let's say, a point over here, which is here, I would walk backwards along the vector field for a unit time, for example, figure out where I was, I'm over here, and that's the value that I assign to this position, right? So that's all this equation is saying. Right? I define the position, the value at some point, I walk backwards along the vector field. So I'm thinking of the vector field as moving the signal forward to figure out the value. I do backwards mapping and sample from there. Okay. For small enough t, what happens? Well, if we take a very small time step along the vector field, what are we doing? We're just moving, we're taking a step in the vector field direction, right? So what we're going to do is to get the difference between the advected signal and the original signal, well, that's the original signal over there, and here we're just going to move backwards just by the vector at that point, scaled by t. Okay, it's sort of a linearization of this process, and you can reinterpret this as if I want the difference along, if I want to know how much my signal changes as I move along a particular vector, in this case minus t times v, that's just the gradient of the signal dot producted with t times v. Right? So that's this expression, and so in a sort of a more continuous formulation, it tells us that if we're performing the advection with respect to time variable t, then the temporal derivative is minus the gradient of the signal dot producted with the vector field. Okay. Good. Good. So that's sort of stuff in the image domain. Now we want to work not in the image domain, we want to work on surfaces. And so we need to translate this machinery into something that we can apply on surfaces. So we have the Screen-Poisson equation, right? So we have some signals, we have some vector fields, we have some operators. What happens here? Well, so the signals, f and g, these are values most likely that live on vertices. Not very hard to discretize. At every vertex in your mesh, you have a value. Your vector field, depending on who you talk to, Keenan will disagree with me, but for example, you can think of it as a constant tangent vector in each triangle. So at each triangle, you have a vector, which is the direction that the vector field is going. You also have, you need to discretize sort of what looks like the identity operator. And here the idea is really the following. You're trying to solve an interpolation problem where you're trying to balance, my function has to match the value of g, and it has to match the gradient, its gradient has to match v. But this sort of this matching penalty is not uniform. So depending on how big your vertex is, how much area there is around it, it's more important or less important to match the value. So you have this, the identity operator, which sort of dictates how the matching happens, is weighted by the importance or the size of a vertex. This is sometimes called the mass matrix. It's a diagonal matrix. And in it, you store 1/3 of the areas around the vertex. You also want to do, to sort of match the gradient part, you need a Laplacian. Typically, a Laplacian is a measure of how much your function differs from the average of its neighbors. on a uniform grid, that's pretty straightforward. You just average your neighbors. But here again, you have non-uniformity in your mesh. You need to take into account how your neighbors are distributed around you. And so you need to take into account the angles. This is typically in the discretization gives you something called the cotangent Laplacian. And the last one is this divergence operator, which is also not particularly hard. I won't belabor that. What I will sort of zoom in on a little bit is sort of the construction of these mass matrices and stiffness matrices that require computing areas and angles. One way to do this, one way that I like to do this, is you consider each triangle in turn, and you think of the map that takes this unit right triangle to this triangle, right? So there's some deformation in this. And that defines a metric on the unit right triangle. You can say, I want to work on this unit right triangle. I have a metric which is induced by the embedding of this triangle over here. Okay? And what that means in practice is I can forget about the embedding itself. As long as I have my metric, I can compute the quantities I need. If I want the triangle, I can use the metric, in this case the determinant. The square root of the determinant of the metric will give me the area. And if I want the angles for the cotangent Laplacian, I can compute them similarly. Sort of straightforward, just using this metric. Okay. So that's the discretization of this screen Poisson system to meshes. The other thing we need to do is flow lines. What we'd like to do is we have some point P, and we'd like to compute where we go as we follow the flow. Okay? So what we're going to do is we have a vector field. We'll sample it at the point P, and we'll take a step forward along the vector field. That's perfectly good. Now you're at some other point on the surface. Where you run into trouble is if you happen to have to take a step that takes you across the edge. What you do in that case is you simply take your mesh, you unfold it along the edge so that everything is straight and flat. You now have a perfectly well-defined point on the adjacent triangle, and that's your advected position. So that's flow lines for you. Good. Sorry, there we go. There it is. Okay. So those are our building blocks. People are good? Okay, so now we're going to apply these to a number of different problems. So here's a classical problem in image processing. I've gone out with my camera, I've taken pictures of an environment, and here they are. I've managed to register them somehow. I don't know how. There's some black box software that'll do this, maybe using SIFT descriptors, I don't know. And I have this image, right? And the problem with this is that as I take the different images, my camera might turn on the exposure by different amounts to account for the fact that part of the scene is bright and part of the scene is dark. And I get these very visible seam discontinuities across the boundaries of these image tiles. Okay. So what do I want to do? I want to do something very simple. If I look at these tiles individually in the interior, everything is good. Things are changing the way I want them to. At the boundaries between these guys, things are changing incorrectly. There's this sharp discontinuity. So what I'm going to do is I'm going to create a new characterization of the change, a new target gradient field. In the interior, it's exactly what it was before, because that's good. Across the seams, where we have this large discontinuity, I'm just going to say the gradient should be 0, or the tangential component, or the normal component should be 0. So instead of changing abruptly, instead I'm saying there should be no change at all. Okay. That becomes a screen Poisson equation, or just a Poisson equation, very of the format that we saw over there. And you see that when I solve this, all the seams go away. Okay. Does that make sense? So there's no reason that I'm restricted to doing this on meshes. I have the apparatus to transform this sort of processing to surfaces. So for example, I have a 3D surface that I've scanned. I've imaged it from different perspectives. I have exactly the same problem, that if I overlay the individual images, I have discontinuities due to changing in lighting or camera settings from image to image. And you can see the discontinuities in this image. So again, I'm going to play exactly the same trick. I'm going to grab the gradients from the individual tiles. In the interior, that's my target gradient field. Across the seams, I'll just set it to 0 so that there's no change. And I solve this system, and I get a seamless texture. Okay. So that's one way to do this. Another application, I hinted at the fact that gradient domain processing is powerful for a number of different things. So another application is going to be image sharpening. So I have an image, and I want to bring out the details, and hopefully, again, this monitor will allow us to do this. So what do I want? I want an image that, first of all, looks like the original. because qualitatively it should look like the same image. But then the other thing I'm going to want to do is I want to exaggerate changes. So instead of having the gradients of the new image match the gradients of the old image, I want the gradients of the new image to match the scaled gradients of the old image, to sort of amplify the change, right? So again, I have this value fitting term, this gradient fitting term, and assuming that I make beta bigger than 1, I'm going to accentuate the gradients, going to make them larger, and you see that the details are coming out. Globally, you sort of have the same qualitative feel of this swan image. That's the value fitting term. But if you focus on where there's abrupt changes, we're trying to make those changes even more significant. Good? So again, principally, there is nothing about this that is restricted to images. We can play exactly the same trick. If we have this discretization machinery, we can play the same trick on surfaces. If I want to bring out the detail in the surface, I can just amplify set beta bigger than 1. And again, I have qualitatively the same values, but boundaries are more pronounced. I could also go the other way. I could set beta to be less than 1. I can dampen the gradients. And not surprisingly, you get a smooth version of your input. And if you take this to the limit, if you set beta is equal to 0, this is actually very closely related to heat diffusion on surfaces. Okay. But why stop there? We don't just have to work with signals, colors on meshes. At every point on the mesh, we have a signal which is the position of the mesh in 3D, the x, y, and z coordinates. So instead of processing a signal on the surface, we can process the surface itself. Okay? Exactly the same trick. If I use beta bigger than 1, I will accentuate details. If I use beta is less than 1, I'm going to dampen them. So I can do smoothing or sharpening. And again, similar trick. If I set beta is equal to 0, this is very closely related to mean curvature flow, which is a smoother of surfaces. Okay? Good. Good, good, good. And I can push on this still further, right? I have this formulation over here that says I want to minimize the difference between f and the input, between the gradient f and the scaled gradient of the input. And I'm balancing my value fitting with my gradient fitting using this parameter alpha, which says how important is one over the other. Nothing says that alpha has to be a constant. Alpha can be spatially varying. So in some regions of the mesh, I can have my surface sort of give precedence or importance to value fitting. In other places, I can give precedence to gradient fitting, right? So for example, in this result, what I did is I set alpha to equal to be some measure of the curvature. Okay? So what I'm saying is when the curvature is high, so I set beta is equal to 0. So beta is equal to 0 sort of does smoothing, but I'm saying when the curvature is high, value fitting dominates, preserve the original signal. When the curvature is lower, do some more smoothing. And so you'll get something like that. So that's your input over there. Without any biasing or anisotropic diffusion, I'm going to get this. The details on the eye are washed out. Here I get something that preserves the details, the geometric details, while still smoothing the surface. What else do I want to say about this? Do I want to say anything about this? Implementing this is almost straightforward. What you end up doing is alpha becomes a diagonal matrix. You have to throw in an additional diagonal matrix into your system. Other than that, nothing really changes from what we talked about before. For those of you who do geometry processing, you can think of this as a conformal deformation of your surface, nothing more. Okay, good. If you're wondering why, I'll answer that question later. The second one is line integral convolution. So people are okay with the first one? Again, if you have questions, I'm happy to pause and answer. Okay, line integral convolution, right? So this is a work that goes back at least almost 20 years rather. I have a vector field. I would like to visualize it. So what am I going to do? I'm going to start off with a random signal, a purely random signal. And then I want to change this random signal to assign a color, a new color at each point. So what I'm going to do is I'm going to pick a point, and I want to compute the value at this point. So what I'm going to do is I'm going to follow the flow lines backwards and forwards along, follow the vector field, along the vector field. So here I'm going backwards, I'm going forwards, I get a curve. And what I'm going to do is I'm going to replace the value at this point by some average of the values along that curve. Okay. And I'll do this for every point, and hopefully I'll get something like that. So again, there's nothing principally about this that is restricted to the context of image processing. All this requires is that you can walk a vector field. We know how to walk vector fields on images, but we also know how to walk vector fields on surfaces through this unfolding process. Nothing fundamentally harder about doing this on meshes, but this could be time consuming. I haven't actually done the test, so I'm not sure. So I will propose another way to do this instead. Okay? So let's take a look at our heat diffusion equation that we saw before, where we said beta is equal to 0. So you want your initial signal f to match the old one, and you want the gradients to be close to 0. You run that, and you will get something like this. Right? Just a diffused image, and depending on what alpha value you use, you'll get more diffusion or less diffusion. You can think of this as a time step in a heat diffusion PDE. Okay. But now we have a vector field, right? And our goal is not to just blur things. Our goal is to blur things along the flow lines. Right? So how are we going to do this? What we're going to do is something very simple. We're going to take our image over here, and we're going to stretch it in the perpendicular direction, the direction perpendicular to the vector field. Okay. Then we're going to smooth, just like we did before. Right? Just solve this heat diffusion process on this smoothed image. Okay. And then we're going to compress back. And there you go. What you see, hopefully, is you see this line integral convolution of this visualization of that vector field, where you get these streamlines. They're moving vertically. Because these were, you could sort of think of these as radially symmetric blurs over here, but when I compress it back down, they become very ellipsoidal. They compress down into these long, skinny stretches. And of course, the more I stretch this image, here I think I had to stretch it by a factor of 40 just to get something reasonable. The more I stretch it, the thinner they're going to be. Okay, so that's good. So we can do this to surfaces, right, by just taking the surface and stretching it in the direction perpendicular to the vector field. Okay. Now what does that mean? I don't know what that means. I'll be honest, I don't know. But we don't have to know is the point. It really doesn't make a difference. We don't have to stretch the surface. We have a measure of distance on the surface that we talked about, this metric that comes from the embedding. We can change the metric without worrying about the embedding. I can just distort the metric itself. Okay. That I can do easily. And then I solve exactly the same screen-Poisson equation that I solved before, but now when I define my mass matrix and my stiffness matrix, I define them with respect to this distorted or stretched metric. Not fundamentally different than anything I did before, exactly the same computation, just the metric on each triangle is different. So for example, if I took my vector field to be the principal curvature directions, the maximal curvature directions, I'll get something that looks like this. Okay. Good. So that's sort of the second in the set of things that we're taking, and we're sort of taking these image processing techniques that we know and sort of reinterpreting them a little bit. In this case, we had to do a little bit of manipulation. That's going to be sort of the pattern we're going to follow in the next two applications as well. We need to twist it a little bit, and we get something that's easily generalizable to surfaces. So even earlier than line integral convolution, we had shock filters from Osher and Rudin. And the idea is you have a signal, and you want to sharpen it. And you have some goals in your sharpening process. You would like to preserve the extrema. So when there's a local maxima, you want it to stay a local maxima. When there's a local minima, you want to maintain the local minima. But you want to make sort of the changes between local maxima and local minima sharper. So if you're thinking of this guy sort of concave down, concave up region, you want to push the values in the concave up region down. If you have regions that are concave down, you want to push their values up, right? And you're going to solve some sort of partial differential equation that'll look something like this. Okay. So let's try and formulate this as a partial differential equation. So we're going to have two parts. We're going to have the change of our signal with respect to time, and we have two targets. One is we want to preserve the extrema, so that's going to get encoded in this guy, and one is that the edges become more pronounced. Okay. So what does it mean that extrema are preserved? It means that where there is no change at a plateau, right, where the gradient of the function is 0, this guy shouldn't change. We don't want the function to change where the derivative of the initial function was 0. Okay? So a simple thing to do is just to make this f function just be the square norm of the gradient. That would force this product to be 0 anytime the gradient is 0. That would mean that your critical points are not moving. Okay. The other one is sort of, we talked about this, you want to take concave up regions, push them down, concave down regions, push them up. What does that mean? We want to look at the second derivative. And okay, in one dimension, you just really want to look at the second derivative. There's nothing to do. In 2 dimensions, you want to look, the second derivative is a matrix. You really want a value. So you would say, let's take the second derivative along the gradient direction. So that'll look something like that. Right? And you get this partial differential equation. Roughly, this is what shows up in Ocean-Rudin. And you solve this partial differential equation, and due to CFL conditions, you need to take appropriately sized time steps, and they kind of have to be a little bit small to make sure that you don't overblow your values. But fine, if you do this with enough care, and this is sort of what this work talks about, you can get nice results. Okay? So we're going to reinterpret this equation. All right, so here we go. We're going to rewrite this PDE. So, okay, so here we have this change in time of their signal is the product of these two guys, the square norm of the gradient, and the gradient, or the second derivative, along the normalized gradient direction. Okay, so I'm going to rewrite this guy over here. I'm just going to re-express it, and it looks something like that. Okay, so if you do this, this is I normalize by the square norm of the gradient of the Hessian of the function in the gradient direction, dot producted with the gradient. That's exactly the same thing. Good. But the nice thing about this is if you look at the product of these two, you have the gradient term over here, the square gradient. You have 1 over the square gradient. In your expansion up at the top, they cancel out. Okay, that's good. That's very nice. Now what is this? Well, this is, we've seen this before, this is the expression for advection, where we're advecting the signal, f, along the vector field defined by the Hessian times the gradient. So if we compute the Hessian, the gradient, and multiply it by the Hessian, that gives us a vector field. We are now advecting along that vector field. And if you want to expand this out, so this is a little bit ugly. We don't really like this in discrete differential geometry. It requires 2 derivatives. But you can write this out a little cleaner as take the square gradient and take the gradient of that. That's the Hessian times the gradient. Okay. So let's actually see what's going on here. So what am I proposing we do? We start off with an image f, right? And we want to advect it along this vector field. So first of all, we're going to define this potential, the square norm of the gradient. That looks something like that. That's going to be large. That's going to be large where there's large changes. It's going to be 0 in regions of constant value. Then we want to define our vector field. So our vector field is the gradient of this guy. So there it is. We take the gradient of the potential, or half the gradient of the potential if we're careful. And then all we're going to do is we're going to advect our signal along this vector field. Okay. All right, so what's happening here? So we're doing advection along this vector field. We're moving things along the vector field, right? And so what does the vector field do? It points from regions where the potential is small to regions where the potential is large, right? So what is the region where potential is small? That's where the square gradient is close to 0. So it's going to take values where the signal is reasonably smooth, and it's going to push them towards regions where the gradient is large, towards the edges. So it's going to take your values and try and push all them, sort of squeeze them towards the boundaries in your signal. Okay, right? Because that's where the maxima is of your output. And so what you get is a representation or a new image where sort of the constant, which is almost piecewise constant, where you're taking really smooth parts of the image and pushing them towards the boundaries, the interfaces or the edges in your image. Good. So here's an example of such an image, right? So here's a giraffe in Tanzania. And on the left, you see the zoom in of the original image. And here's what you're going to get after you run shock filtering on this. Okay. Very nice, I think. Again, nothing about this is fundamental to images. This requires taking gradients. This requires taking advection. We know how to do this on surfaces. So we can do exactly the same thing for a signal on a surface. So here we have colors on the surface. We play the same game. And there's the zoom in over there. And here you can almost see it I apologize for the projector, but maybe you can see that sort of the boundaries here are really nice and crisp as opposed to what they were before. But why stop there? There are other signals you can define on a mesh. So for example, if I have a mesh, I could take the signal to be the normals. At every vertex I have the normal. Every face I have a normal, fine, whatever. I have the normals, and I can play the same trick. I can try and advect the normals along the gradient of the square norm of the gradient of the normals. Good. And then I can reconstruct the surface from the new normals, and I will get something that looks roughly like this. Right? So I'm going to get a new signal on my surface. I had my old normals that change smoothly, and I'm going to try and push them so that the change in the normal happens abruptly. It happens at sharp creases, and everywhere else the surface has constant normal, which is to say a piecewise flat surface. I have these new normals. I do have to solve one more problem to get back a surface from these new normals. That turns out to be a Poisson equation, not unlike what we saw before. Good? Okay. And one more, optical flow. So I have to be careful about what I say here. I'm going to say something wrong, and I apologize in advance, but let me give the motivation for this. Our motivation for this came from a larger project, which was based on this video textures work. Again, you can't really see anything, which is unfortunate. You had a video, a short video, I think it was 5-10 seconds long, of a candle. And you wanted to turn this into an infinite video. So what can you do? Well, you can just loop your video. But looping your video has two problems. Looping your video has the problem that when you get to the end and you jump back to the beginning, you get a significant discontinuity. There's a pop in your video as you jump from the first frame to the last frame, from the last frame to the first frame. The other problem is that it gets very monotonous. Right? You're just seeing the same thing over and over again. So what was proposed in this video textures work is to do the following. Take your video and take a frame and find where do you see a similar frame, or maybe a couple similar frames. So you have a window, maybe 3 frames. Where do you find 3 similar frames in your video? And if you can find a good match, that's a potential jump. So instead of playing your video linearly from the beginning to the end, at this point where you have these corresponding frames, you just jump. You have enough of these jumps. At any point as you're playing your video, you can decide, do I play forward or do I make a jump? And you can toss a coin. You get rid of the discontinuity problem because you've made sure that you're transitioning to something that looks like where you came from. You get rid of the repetition problem because you're flipping a coin randomly at any particular point to decide whether or not you make the transition or stay with the original. Okay. Our goal is to do this on surfaces. Right? So you have a surface or an animated sequence of surfaces, and you want to do exactly the same thing. And so here you see this red dot. It's following the line of the video frames, except for when it arcs along these arcs. These are these alternate arcs that we've constructed. Hopefully, if you're watching this video, you do not see when this happens. You don't see the transition. You can't distinguish between sort of content that's actually captured and content that's synthesized. And again, you can play the same game. You can play the video over. You can have infinite content without repetition. Okay? So that's the game we need to play. There is a lot to do to make this happen. This is a huge system that was put together by one graduate student, bless his soul, that required doing a lot of different things. You need to identify when you have 2 sort of windows of action that look the same. So there's a shape matching problem. There's a deformation or registration problem. You need to sort of map a common triangle mesh to both of those so that you can sort of talk about those being parameterized over the same domain so you have some way of transferring detail. You need to interpolate geometries to synthesize these in-between motions. And then these geometries have texture on them. You need to somehow transition the textures so that those flow smoothly. And we will only talk about the last one. Okay? Only about interpolating textures. So you have surfaces. They have the same geometry because you've solved template fitting and geometric registration problem. They have the same geometry, and all you want to do is get their textures to align. Okay? So here's an example. I have 2 images, and I want to synthesize a transition between them, right? So one thing I can do is I can, of course, linearly blend between them, right? And that has all sorts of ghosting artifacts and looks terrible. Things fade in, things fade out, there's no motion. So what do? What is sort of the classic solution is you take these two images and you compute the optical flow field. How do pixels move from one image to the other? Then what I'm going to do is I'm going to start at my source and I'm going to follow the flow field a little bit, sample through the advection process that we talked about, get a new image, follow a little further, get a new image, and so on and so forth. And there we go. Right? So there's the optical flow blend of this. Right? Good? Okay. So how is this done? So this is done using traditional optical flow methods, right? You're looking for a vector field that takes the source to the target. Or another way to say this, if you want this in a more symmetric way, is if I move the source forward along the flow by half the distance, half a unit time, and the target backwards along the flow, they should match up. That's my goal. Right? So this is the energy I'm trying to minimize. And again, sort of we have this discretization of what happens when you advect by a small amount, or this linearization, and you get this expression which says, okay, that there's the gradient term that's sort of you dot product with the vector field, which is the flow field you're trying to solve for. You're trying to get things to line up. And this is looking a little bit like a screened Poisson equation that we saw before. Okay? Now, solving the optical flow problem is, as you know, under constraint. There are many solutions. There's no unique solution, or it's not a convex problem. That's probably a better way to say this. There are many different solutions. You can think of, if you have a checkerboard pattern, you can translate it in many different ways to get things to register. There's nothing canonical about the solution that you get. So typically what you do is you solve this problem hierarchically. Right? And you want to solve this hierarchically for two reasons. One is you sort of want to get something that sort of does as little motion as possible. The other reason is this linearization is only good locally. So you kind of want to restrict yourself to sort of moving things around only a little bit. You don't want to do big motions and approximated by a linearized model. So what do? You do things hierarchically. So let's say you have a vector field. You'll apply that to your source and target. You'll move your source forward. You'll move your target backwards. And then you'll look for a small motion, a small vector field that will bring the source and target closer to each other, more localized. Okay? You'll add that to the vector field that's already describing the flow, and then you'll advance to the next level of your hierarchy to get the still finer motions, and you repeat in this process. Okay? And sort of what's nice about this is if you take a hierarchical representation of your image through some sort of pyramid, right? What happens is at the lower resolutions of your pyramid, you're necessarily working with smoother images, because you've downsampled, and smoother vector fields. They can't change as abruptly. You don't have that many degrees of freedom. Okay? But the problem is that for meshes, we can't do this. We don't necessarily have a nice hierarchical representation of triangle meshes in general. So you can't represent the signal hierarchically. So what we're going to do is, instead of forcing this implicitly, we're going to encourage this in a soft sense. Okay? So what do we need to do? We need to smooth our signal. Well, we actually know how to do that. Right? So what we're going to do is we solve a screened Poisson equation, where again we want the source, the new source, to match the old source. We want the gradients of the new source to be close to 0. And this weighting term over here is going to be proportional to the level. So at a very coarse level, at sort of the lowest resolution of the hierarchy, we want to give strong weight to the gradient interpolation. We want this to be as smooth as possible. As you move up the hierarchy, you're going to have a less and less smooth image because you sort of have finer details to work with. And you'll do the same thing for the vector field you're solving for. So here's the brightness constant term that we saw before from the Lucas canonic formulation. But we're going to throw in one more smoothing term. We're going to say we want the vector field to be smooth. Because again, we're not working in a low dimensional, low resolution space. Vector fields can be high resolution by construction. So we need to force this explicitly. We want the gradient of the vector field, the change of the vector field, to be small. And how small it is will depend on where in the level of the hierarchy we are. Right? At the coarsest levels, we want a really smooth vector field to get sort of the larger parts of the flow. As we move up in the hierarchy, we want this, we allow for a little more finer resolution of the vector field to capture the finer details. Okay? And both of these just involve solving a Poisson equation. This is a little bit of cheating. This is not quite the standard Poisson equation. This involves a Laplacian not on scalar fields, on vector fields. I haven't really talked about this. This is the Hodge Laplacian, or if you want, you can use the connection Laplacian. I think either of those will work equally well in this context. But it's basically what we were talking about before. And so here we go. We have these two models that we've discovered in our sequence that look similar to each other. They're not identical. So we need to register them to each other. And so here they are. We've aligned them to each other. We've performed a non-rigid deformation that gets them as well aligned to each other as possible. And here's the in-between pose. They're both, this is used as a template to represent these two guys. And what we have is we have the two faces. Oh, this is very hard to see in this image. This is unfortunate. And we solve for the optical flow, the vector field that best aligns this texture to that texture. Sorry, this texture to that texture. Ooh, this is bad. Let's see if this is better on the next image. Okay, and so on the left, what you're seeing is, again, what's happening with the linear blending. You see stuff like the eye is blurring in and blurring out. I think you guys can see this, yeah? On the left, on the right, you're seeing the results of optical flow. The optical flow has correctly figured out that the vector field should drag the eye in the source to the eye in the target, and it's following that flow as the eye is winking. Okay. Good. People can see this? I hope people can see this. Yeah?
You can't hit the lights.
Let's try and hit the lights. It's not clear that I can hit the lights. Oh. Nope, nope. There we go. Is that better? So you guys can see the popping artifacts that are happening on the left when you're just doing the linear blend, and when you're advecting the signal on the surface using the optical flow field that you've discovered by solving this hierarchical set of Poisson equations, you're getting this nice deformation of the texture. The geometries are the same. They're both defined over the same exact triangle mesh, and how we do that we're not going to talk about. But what you're getting is a nice transition. Okay, good. So that takes us really to the end of the talk. So what this work was about is, there are these fundamental operators. In this case, what we saw was screen Poisson equations and vector flows, flow fields. And let's say we have them. Let's say we somehow miraculously have them on surfaces. Well, what that means is that we can take well-established image processing techniques and they translate directly to processing of signals on surfaces. Right? We didn't have to do anything fancy. We did a little bit of reinterpretation of certain problems. We reformulated shock filters as an advection rather than as a PDE. We reformulated optical flow instead of this hierarchical solve as this sort of constrained solve where you're successively loosening the constraints on the vector field and on the signal to allow yourself to capture finer and finer details as you move up the hierarchy. But fundamentally, we're solving the same problem. And what's nice is, that this isn't my work, right? These techniques for working on geometries are well-established techniques by really good people in the geometry processing community. All we need to do is take those tools and use them to transform or translate existing methodologies to surfaces. The other sort of takeaway that I have is that if you work on images, it's really nice. It's really nice you have regularity. Things that are easy become so much easier, right? You can take advantage of this regularity. You can have parallelized out of core multicoloring, temporal blocking, whatever you want. You can define hierarchical representations through upsampling and downsampling, all straightforward. You even have fast Fourier transforms that take advantage of this. All really good. So things that were easy, they just get easier. For meshes, that's not the case. Things are hard. You have to work with this non-uniformity. It's implicit. You have to work with this metric. But once you have that, things that were hard become no harder than the things that were easy. Right? Doing anisotropic distortion of your metric for line integral convolution or for doing edge-aware based sharpening is fundamentally no harder than just doing isotropic diffusion. Everything's anisotropic by construction. Everything's irregular. So nothing is easier, nothing is made easier by trying to keep things regular. So it's sort of nice. You can do harder things once you've wrapped your head around doing the geometry processing and they become easier. So that's really all I have to say for you. Most of the stuff is described in these 3 papers. As Keenan had mentioned, I tend to release my source code. So source code for a lot of this stuff is also available online. Thank you for your attention.
Okay, any questions for Misha? So I'll start with one, and maybe just a comment that you make this look so easy, but I think you sell yourself a little short because you start out thinking about image processing in a way that not everybody necessarily does, which is in terms of PDEs, right? Which is a popular way, but not everybody thinks about it this way. So in some sense, it's really this idea of formulating signal processing problems in terms of geometry and PDEs from the beginning that allows you to translate it so easily to vectors.
Sometimes. So in the case of shock filters, I try to walk away from the PDE formulation of shock filters and do it instead as an advection.
Right.
I mean, it's also a form of, right, it's a method of characteristics, and right, but it's just sort of, I'm trying to get away from actually solving a partial differential equation, a highly nonlinear partial differential equation.
Right. Yeah, and the flip side of this is that somebody who's not familiar with these tools might say, boy, this sounds like a lot of work. I have to learn about PDEs, I have to learn about geometry. Why don't I just stick to, I'm comfortable with image processing. Why don't I just stick with voxel grids when I go to 3D? Right? This sounds so much easier. So there's always a question, how much of this is really you benefiting from working with these geometric formulations, mesh formulations, and how much of it is, okay, we're having fun playing these games, but you could actually do something quite similar with voxel formulations.
So I would say this. I would say the moment that you want to really leverage anisotropy and inhomogeneity in the system, it's not true. It is certainly, let me think about this. Perona and Malik in the early 90s, right, have this anisotropic diffusion work, which is sort of transformative for image processing. They certainly look at it, but what makes it hard to do what they did is exactly the fact that you're giving up regularity, that you're changing your system from being a homogeneous system to an inhomogeneous system, and even an anisotropic system. For us, it's no harder. And so we don't have to bend over backwards to get that sort of stuff to work. We can really build that in. So I think in the context of doing working on voxel grids, I think you can. I wouldn't say that you can't. I think there are level set methods where you represent your surface as a distance function, and you have the property that sort of, if you take a look at the Laplacian, it's reasonably easy to formulate because the normal component cancels, and you can do diffusion directly in voxel grid. You have the disadvantage that you're now solving a three-dimensional, or in an n-cubed space, you're doing sort of diffusion instead of, but you have regularity versus doing this on a mesh, which is fundamentally n squared. But you can do it. Or, you can do sort of narrow band method, so you don't actually have to solve in the entire system, but it can be done. But you really sort of, you're still stuck with some fundamental notion of regularity there, which we get to ignore.
Any other questions?
I guess for the optical flow part, a dumb way of doing this would be, you unwrap your texture and go to VMAP, do optical flow and your VMAP.
Well, so there's two problems with that. One is distortion. Naturally, you have to contend with distortion. Bigger problem is if you're doing UV maps where you have a multi-chart atlas, then you have to deal with seam continuity. What happens if you go across one seam and you jump to the next seam over there? How do you transport values? Can be done. Wouldn't say that it can't be done, but it's hard. It's hard. So I think those two in conjunction make it hard to do optical flow. Whereas again, nothing fundamentally hard about what we're doing here. Just throwing in a couple of more smoothing terms, one for the signal and one for the vector field. Otherwise, we're solving the same type of system. Yeah?
So full disclaimer, I don't do any of this stuff. I'm just kind of wrapping my head around it. So this kind of non-homogeneity you're talking about in meshes in 3D, is the kind of analogous thing in 2D something like a vector image or something you use in Inkscape or PowerPoint or whatever, kind of not using pixels but using some other more, I don't know, non-homogeneous representation of the things you're seeing? Is that fair way of looking at that?
I would say mostly, with one caveat. So I think you're right. You can look at sort of polyline representations or polygonal representations of curves in 2D. And the only difference there, I would say, is that when you're working with surfaces, or when you're working with curves rather, you can have arc length parameterization. You can actually have your discretization be somehow regular by construction. That's not possible when you're working with meshes. So you can't really get an arc length parameterization over some base domain of your mesh because then you don't have curvature. So things get fundamentally hard with surfaces because there's curvature, because you can't have uniform parameterization, non-distortionary parameterization.
Okay, so Misha will be around for a bit if people have more questions, and otherwise let's thank him again.